This lesson, entitled Le Chatelier's Principle and Chemical Equilibrium, looks at the qualitative effect of putting a stress on an equilibrium. It states that if an outside influence upsets an equilibrium, the system undergoes a change in a direction that counteracts the disturbing influence and, if possible, returns the system to equilibrium. These stresses, or the outside influences that we are going to study, are adding or removing a product or reactant, changing the volume in a gaseous equilibrium, changing the temperature, adding a catalyst, and adding an inert gas at a constant volume. The first one we'll examine is the effect of adding or removing a reactant or a product to a system. When we add a substance to the system, we're going to be increasing the concentration of that substance. So for example, if I add NH3 to the system, I am going to increase the concentration of the NH3 in that system. The stress on the system is that there is excess NH3 in the container. And the way that the equilibrium is going to counteract that stress is by using up the excess NH3. The only way to do that is to produce products or convert the NH3 into NH4 plus and OH minus. Therefore, if we increase the concentration of the NH3 in the system, the equilibrium is going to shift to the right. It will shift to the right until it's able to achieve a new equilibrium. That's an example of adding a reactant to the system. I can also look at an example where I add a product to the system. So I add, for example, some NH4 plus. In this case, the stress on the system is that there is excess NH4 plus. The system wants to counteract that stress, and the way that it will do that is by using up the excess NH4 plus, which will occur if the equilibrium produces more reactant or shifts to the left. Another stress can occur if we decrease the concentration of one of the reactants or products. So for example, I might decrease the concentration of NH4 plus. The system will counteract that stress by trying to replace the missing NH4 plus, and will do so by allowing the forward reaction to occur or shifting to the right. Similarly, if we decrease the concentration of the OH minus in the system, the stress is that we are missing some product. The system wants to replace the missing product and therefore will shift right in order to do so. The goal ultimately will be to return the system to a new equilibrium. The second scenario that we'll examine is changing the volume in a gaseous reaction. If you've got an equilibrium where all of the reactants and products are gases, we can examine the impact of changing the volume on the system. What we need to remember is that the volume of the gas is proportional to the number of moles of the gas, as stated from Avogadro's hypothesis. When we look at this system of 1 mole of N2 reacting with 3 moles of H2 in equilibrium with 2 moles of NH3, we can look at the impact of increasing the volume, which is the equivalent of decreasing the pressure. Okay, so if we increase the volume or decrease the pressure of the system, this will be a stress on the system. And the equilibrium is going to want to shift in order to counteract that stress. When we think about increasing the volume, we can think about giving the equilibrium more space. So if we give this reaction more space, what it's going to want to do is use up that space that it's been given. In order to use up the space, it will need to produce more gas. So the way we study gaseous equilibrium is to look at the number of moles of gas as reactants and as products. In this equilibrium, we've got 4 moles of gas as reactants, which are equivalent to 4 volumes of gas, as opposed to 2 volumes of gas or 2 moles of gas as the product. So therefore, if suddenly this system has more space by the increased volume, what it's going to want to do is shift to the side of the reaction that contains more gas molecules, because that's how the system will counteract the stress of the increased space. So in this case, increasing the volume will cause the equilibrium to shift to the left. The opposite is true if we decrease the volume, which in turn is the same as increasing the pressure. If we decrease the volume, the system's going to want to shift so that it takes up a minimum amount of space to counteract the stress of the increased pressure. In this case, the product side has 2 volumes of gas, which will require less space, and therefore if we decrease the volume or make less space, this equilibrium is going to shift to the right in order to counteract that stress. The key here is that you need to look at the number of moles of gas on the reactant side and the product side in order to make your decision of the impact of increasing or decreasing the volume. The next stress we'll examine is looking at the changes in temperature, the effect of increasing the temperature or decreasing the temperature on the equilibrium. Now, what is important for us to review is the difference between an exothermic reaction and an endothermic reaction, because it is the type of reaction that's going to help to decide the direction of the shift. Okay. When you have an exothermic reaction, that's a scenario where heat has been released. Okay. And therefore, heat is a product. In an endothermic reaction, it's one where heat has been absorbed by the system. So we can think in this case of the heat as being a reactant. Now, what's important to note is that there is a term, delta H, which is called enthalpy, which is used to report whether a reaction is exothermic or endothermic. And you're going to often be given the enthalpy of the reaction, and you're going to need to use that to decide if the system is exothermic or endothermic. A negative sign on a delta H means that the reaction is exothermic, and a positive sign means that it is endothermic. At this stage, it's something that you just need to know. We are going to study enthalpy in great detail later on in the year, and we'll explore why exothermic is negative and why endothermic is positive. For now, it's important to just know the signs and what they mean. We looked at this particular equilibrium, N2O4 in equilibrium with 2NO2. And I heated it up and I cooled it down, and we saw the effect of that. We saw that when we heated it up, the equilibrium actually favored the right-hand side. It produced a darker color or more of this brown NO2 gas. When we cooled it down, it favored the reactant side, or the N2O4. What we're going to do is explore how the delta H actually could have allowed us to predict that shift in the equilibrium. Really, when we were heating that up, we were looking at an example of Le Chatelier's principle. In this case, we can see, because of the positive sign on the delta H, it's positive 59 kilojoules per mole, we can see that this is an endothermic reaction. So when it's an endothermic reaction, that means that heat is a reactant. The system needs to absorb heat in order to go forward, okay, which is the meaning of an endothermic reaction. So I'll often encourage you to take the information from the delta H and insert that information as a heat term, a reactant for an endothermic reaction. Now in this case, if we look at the impact of increasing the temperature, when we increase the temperature, what we're essentially doing is adding heat to this equilibrium. Heat in this case is a reactant. The stress is the added heat into the system. As we know from Le Chatelier's principle, if we add a stress, in this case heat, the equilibrium is going to shift in order to counteract that stress. So if I add a reactant, the equilibrium is going to want to use it up. So therefore, in this case, it's going to shift to the right towards the NO2, okay, which makes sense from the demo we did. It went darker because more NO2 was being produced. So in this case, if I increase the temperature, I'm going to have a shift to the right. The opposite will happen if I decrease the temperature of this system. If I decrease the temperature, it's the equivalent of removing heat. So I'm taking this heat away. If I take the heat away, the system wants to replace it. For this reaction, to replace the heat, we must go towards the reactant side, because that's the direction that's going to produce more heat. So in this case, I'm going to shift to the left if I decrease the temperature. In this second equilibrium of N2 plus 3H2 and 2NH3, we see from the delta H that it's an exothermic reaction because it's got a negative value. So I can rewrite that where I put the heat term as a product, as is the case for an exothermic reaction. For this particular reaction, if I increase the temperature, the equilibrium is going to want to use up the extra heat that I add, and the way that it will do that is by shifting to the left. If I remove heat by decreasing the temperature, the equilibrium is going to want to shift to the right in order to replace the missing heat. Essentially, when you're dealing with temperature, you can think of it the same way as you do with increasing or decreasing the concentration of substances. But in this case, we're simply looking at the addition or removal of heat. The last two effects that we're going to examine are the effect of the catalyst and the effect of adding an inert gas. It's very important to note that a catalyst is something that increases the rate of the reaction, but it's not going to cause any shift in the equilibrium. It's going to increase the rate of the reaction in both directions, and therefore there is no change in the position of the equilibrium. Adding an inert gas, when we refer to an inert gas, it might be something like neon or argon, any of the noble gases. If we add one of those gases to an equilibrium, it's not going to have any effect. We need to treat the addition of the gas as not taking up much space, and so we don't worry about the space that this inert gas is taking up. So there is no change on an equilibrium when an inert gas is added to the system. At this point, you can try examples 11 to 13, and online equilibrium 4 deals with Le Chatelier's principle. Okay, there are also a few great websites that you can use to help you to review the concepts, and we are going to be doing an experiment that will help you to observe some of the shifts that occur based on changes that you make to the systems.